Welcome to this first uh, European time zone series, StarRocks CelerData webinar. This is Sida Shen, and we have a very special inaugural first one guest today. Anton from Fresha is going to talk about his experience with StarRocks at Fresha, real-time analytics, customer-facing analytics. Let's welcome Anton, and the stage is yours.
Okay, thank you, Sida, for a nice introduction. Okay, yeah, StarRocks at Russia, exciting topic. So, I call it like in a funky name, carving streams into rock, because it's literally what we do. We do a lot of kind of like analytics, so it required to make it more real time. So streaming, and then we have a rock solid StarRocks. So cool name. Okay, let's go. Let's start short with non-technical part first. What is Fresha? So it's basically kind of like a modern SaaS platform in wellness, being, and healthcare. So what it means, like in simple words, you want to make a massage or haircut, you need to book it somewhere. So Fresha is actually a marketplace where you can go and get your bookings, and there are a lot of kind of like fancy features. But it also means that people are interested like in various things. So providers, the people that provide services, are interested to get like the nicest user experience for their users, and also need to understand how they do it. And basically this kind of like stuff about how they perform is tied straightly to the analytics. And now I will share kind of like a little bit story about like what we would be talking about. This is kind of like a classical dashboard at Fresha. So it's performance over time. So you can see all the fancy filters, kind of like sorting stuff, kind of like nice columns, UI. So this looks nice, but at the same time, it actually requires a different data to be processed. Sometimes this data can be stale. Sometimes people actually want to see data in real time, and it's actually presents a lot of interesting like challenges. So first challenge is basically you're a customer, like a provider. You want to provide the services. So there are people going and using your services, and then you want to get like how well you actually perform. So how much money you get, how much sales you get, how much, I don't know, like bookings you get, what is your kind of like best performing employee, and whatever, because this is like a decisions to drive your business. And first, it's actually starting like super simple. So what does it mean? You are actually happy to get your data into your email like once in a month and say like, oh, okay, it's actually kind of like, this is a location that is generating the most of the revenue. I need to focus there. I need to hire more people, and that's it. Then you are not happy about it, and you say like, okay, I want the real dashboards that I can use. These real dashboards that you can use, the classical solution is to get some warehouse and do classical BI. That's how it's actually started, like at Fresha. So this is kind of like more full example, what are we talking about. So there is like dashboards, widgets, kind of like bar charts, tables, all sorts of kind of like crazy UX for data that you can imagine. That's how we operate. And yeah, so this is the numbers, so you can get a sheer idea of what we are operating with. So it's 600K bookings per day, billions of CDC events ingested daily, and 3K requests per second overall. So this is kind of like the main table, like bookings, is rather big, and it's constantly like a problems with it. But in theory, it means that like the operational set of data that we usually need to build all this dashboard is around like 1 or 2 terabytes. I mean, like it's not including like some specific dimensions of this kind of like dashboards and queries. But yeah, it's just kind of like a to get you the understanding what we're operating for. We kind of like have a goal. Kind of like first it was kind of like unofficial. Now it's more like unofficial. So we tolerate 1 minute data staleness for real-time dashboards when we actually face them with the users, and we aim for 1 second response time. So what does it mean? It means like a lot of challenge, because the stack that we operated before, it was just kind of like CDC, all the data from our databases with Debezium, get it into Snowflake and run BI analytics. So it worked. Then you prepare your data into some kind of like flat tables, and you just expose it to the users through something. I mean, like there is more to the story, because we actually developed like more sophisticated solution, because some bigger partners, they said like, okay, we are not happy with the dashboards that you provide. We want to actually run our own analytics, kind of like focus on the data that we like. So we developed like a Snowflake data connector that allows these kind of like bigger providers to pay for it and get the data that they want to process by their own analytical team. But yeah, all in all, it's kind of like, yes, it's working for bigger providers, but still it's kind of like, it's like a batched process in a sense. So you just wait for 20 minutes to get your fresh data, and it's not the nicest user experience when your dashboard said kind of like, this is kind of like, I'm showing you the graphs for the data that was kind of like ingested 20 minutes ago. So wait a little bit until you get new data. I mean, like usually it's enough to make kind of like decisions that you wish with your business, but at the same time, it also means it's kind of like ruining the purpose of all these fancy widgets and kind of like bar charts and kind of like uh, lines that are updating in real time. So it's about like user experience still. So the problem that we are tried to solve first was okay. We have some real-time dashboards on homepage on homepage, and they actually show you the amount of bookings, the amount of money that you make, how your locations and employees perform, and the expectations that people usually have is to have it in real time. So kind of like serious challenge. So we tried to ship it with the stacks that we had before. So basically CDC from Postgres to get it to Snowflake, then model with DBT, and it didn't work. I mean, like it worked, but it was kind of like not in the SLAs that we desired it to be. So we needed to deduplicate CDC, because CDCs contains retractions, basically updates and deletes. So you can pre-materialize some data for your dashboards, but then you need to deduplicate it with a fresh stream. So it's some kind of like Lambda architecture in a sense. So DBT batch modeling, as I said, like every 20 minutes at best. Lambda architecture, the solutions that I described, when you need to duplicate like a fresh tail of events with retractions, it's also kind of like taking at best a few seconds. At worst, I think like we are talking about like 20, 30 seconds still. And yeah, we tried it. It didn't work, and there are some limitations from Snowflake about concurrency. There are some ways to overcome them, but still, it's kind of like you need to fight all the time this stuff, so it's not good, and also the cost. So Snowflake didn't work. So what we tried next is, okay, let's not do anything fancy. Let's just leave it with a big overblown Postgres instance that actually can handle all this load. Does it work? Yes. And it's kind of like mostly, well, real time until you get like a crazy amount of joins. So here you can see like a graph that actually presents kind of like a chart, uh, a breakdown of P of latency. In this case, is P99. So it's around 4 seconds. Not that bad, but if you go to look at the bottom diagram, you can see that there are a lot of errors with 500 errors. So what does it mean? It's actually kind of like timeouts. So for some of the partners, we are not actually returning any data, because the request just timeout. Why is that? Uh, it's like so because imagine like how Postgres works. So in order to process your data, you need to load it into your buffer cache. And once your data in your buffer cache, it's actually quick to return. But when you have like some provider that is not kind of like that doesn't have the data in buffer cache, so you need to load it first, and then it would be slow. And these kind of like timeouts, they're affecting our biggest partners. So like our biggest partners that are willing to pay and the most important for Fresha, they were kind of like getting timeouts in their dashboards. So not good. So once again, back to the scope of the problem. 100K daily bookings, 3,000 requests per second, 20 static joins and subqueries are not that unusual in our stack, and around like 100 of Postgres databases as data sources. So we need to find a new solution that would allow us to introduce real-time analytics, but at the same time, we didn't want to actually kind of like only introduce a new tool to solve real-time analytics. We want it to be a little bit better. And if we would have another need, so that we don't need to rebuild our stack. So we were okay to rebuild our platform one time, but we specifically decided that we want to kind of like make it happen one time. And then when we need to add an additional tool, we don't need to start from scratch, think about architecture and other stuff. So this is what we got in the end. It's fairly easy. Obviously, it's simplified. So we have a sources plane where we have the same Postgres databases that are streaming through Debezium, CDC to Kafka. Then we have compute plane. And for compute plane, we use Flink and Spark. So Spark is used for some batch processing, just to deliver the data into the lake, to do backfills and other kind of like stuff. And then we have Flink, and Flink is like an essential part of our platform because it allows us to do all the transformations, joins, and aggregations that we need before data actually goes to the any sink. Then we have Lake Plane, and for Lake Plane we use Iceberg with Lakekeeper and Pymon. And for the things, we have still the same Postgres, Kafka, Snowflake, Iceberg, Elasticsearch, and StarRocks. And in this talk, we mostly focus in StarRocks because StarRocks is an essential tool because it bridges the gap between customer-facing analytics and real-time analytics that we want to use in our dashboards. And also it allows a very powerful Lakehouse analytics. Why it's important, I will tell a little bit later, but it's actually playing nice with this idea that we want to have some tool that would allow us to integrate and be kind of like extensible enough to support different like ways that we want to provide the data and how we want to balance our needs. Because, for example, for real-time dashboards, I'm actually quite okay to pay the most for the data to be quick and low latency. But for example, if the customer wants to access the data that is kind of like 5 years ago, I'm actually pretty okay to say that when you access all data, you kind of like you will get like a worse latency, but it's pretty acceptable because customers are actually not doing this very often, and also they are inherently kind of like okay with the fact that if I'm querying all data, then there needs to be some kind of like complications and processing involved in this. So if it takes like 2 seconds instead of like I don't know 100 of milliseconds, it's acceptable. It also means that in this case, so StarRocks has a distinct set of capabilities that allows to balance this kind of like data freshness and cost requirements. So let's dive in. So literally, what is StarRocks? So StarRocks is MPP engine with a set of features. And the first feature that is actually pretty important is separation of compute and storage. So you have a different set of nodes. So first is kind of like front end nodes that manage kind of like consistency and query planning and coordination. And then there is a compute nodes that are basically workhorses that hold execution engine and cache the data. So this is kind of like the first. So if you need to have mm, more compute nodes to process more queries, it's actually pretty easy to get this because, in a sense, compute nodes are stateless. So you just kind of like use them to cache the data and execute the data. But if some compute node goes down or kind of like new, it's just a question of how you fill the cache, and that's it. Then it's distributed storage. So basically, all the data lives in your object storage. And then compute nodes are only used to cache this data and execute queries. So this is kind of like what I described is shared data mode. There is another mode, and for those of you who are familiar with Lakehouse, I think like it would be more familiar because shared nothing mode is about like that the data is local to your shards, and when you execute the queries, you first need to kind of like prepare this data on your local shards, and then kind of like shuffle, send across, and basically scatter gather pattern. It's not that kind of like elastic in scaling, but still, if you kind of like have the data local to one node and you can shard it by something, it might be kind of like faster than shared data mode, obviously. So first feature that was actually pretty interesting for us was exactly what I was talking about. So take, for example, ClickHouse. For ClickHouse, first that you should do, you need to prepare like white tables with all the data pre-joined, and this allows you to query it fast. With StarRocks, the story is completely different. So it has like a sophisticated cost-based optimizer. And when you do the joins, it actually first tries to understand what is the efficient order of your query execution that would lead to the lowest amount of time to get your query done. So this is a unique feature of StarRocks. It works. I know that ClickHouse has experimental cost-based optimizer as well, but I mean, like it would take time to work. So I think like right now, StarRocks is one of the best systems to actually do joins and kind of like plan to make them efficient and reorder in a sensible manner. Then what we are talking is comfortable ops and integration. So first you have like a fancy new tool, and then you don't know how to get the data in, or it's kind of like very uh, very hard, and you need to do a lot of kind of like engineering work to just to understand how to get the data into your warehouse. So it's not a question with StarRocks because there are kind of like I haven't actually counted how many ways to get the data into StarRocks. So there is a Flink connector, there is like a Kafka connector with routine load and stream load. There is a Spark connector. There is like you can always kind of like connect to external catalog and use the same Spark. There is kind of like pipes that you can use to basically get your data from object storage. So there are a lot of ways to get your data into StarRocks, and usually they work. And if they doesn't work, you can always choose another one. We actually shared the story how we were choosing how to get the data from our Kafka to StarRocks in a series of blog posts written by Nicoletta. So if you want to know more, you can check it out as well. It's very interesting. I advise you. Another set of Another feature is elastic scaling. As I said, like there are two types of nodes, so front end and CN nodes. So imagine that your workload is spiking. So at the beginning of the day, every kind of like our partner wants to open their page and see the metrics. Okay, they do it, and suddenly you have like a spike of requests. So and imagine that you have only like 10 CN nodes, and it was okay. most of the time, but now you need to handle like 3 times more traffic. What does it mean? It means that kind of like you need more compute power. So what you can do, you can have like autoscaler that watches kind of like your metrics that are responsible for scaling, and then decide, oh, okay, I'm getting actually 3 times more traffic. I need to schedule another compute node, and scheduling another compute node is basically, okay, it's they're stateless. So the only thing that I need to manage is basically cache. So you can pre-warm your cache. You can just kind of like allow your queries to get a little bit more stale. You can have some cache like waiting for you, because that's literally kind of like what we do right now. So imagine, for example, that you schedule a new compute node, and then you don't want for your cache to actually kind of like pre-warm. What you can do, you can leave your PVC that is actually waiting for you. And then this new CN node, if there is a kind of like free PVC, it just connects, and most of the cache would be kind of like okay. And only for the new data, this new CN node would need to go to object storage, but also it can reuse some parts from other compute nodes. So this is kind of like a very consistent and easy story to understand. The more load you want to handle, the more compute nodes you need to scale. Then query federation. So this is like a very important and interesting feature, because yes, you can have your data in StarRocks internal catalog and it just works. And then you can have your data in external catalogs, a bunch of them. So you literally can go to your data lakes like Iceberg, Pymon, Delta, Hoodie, whatever, and kind of like query it with the same SQL. You can go to Elasticsearch. You can even go to your database like Postgres database through JDBC connector. And it actually creates an interesting pattern when you can combine data from different data sources in a way that makes sense for your analytics. There are different caching optimizations. So first one is basically the main one, is when you have CN node, as I said, like they have a cache. So this cache is reused, and that's how your data, even though the main storage is object storage, is still fast. But also, I take an example with iceberg caching. So for example, if you want to query your lake, iceberg lake. Oh, my cat is trying to attract my attention. Sorry. Okay, so where I stopped. Okay, imagine you have like iceberg lake, data lake, and you want to query it. So in order to start like doing this, you need to download a metadata, parse this metadata, just to understand what is the most efficient way to get this data into your just to plan your query. So can you do better? Of course you can do. So for example, you can cache these metadata files, and the next time when you return, you don't need to parse them, and it's just a question of reloading cache and kind of like getting a sense when you need to reload this cache. This is very sensible, and it works most of the time because, for example, when you wish to query Iceberg Lake, you can literally say, okay, my iceberg lake is up to date, like for kind of like for the data that is kind of like 20 minutes ago. And you have this guarantee, the data is cached, and you only kind of like reload cache when you need it. And we, for example, use it a lot. Okay, so what it's all about? It's about that StarRocks is a very sensible engine with a set of features that allows you to balance data freshness and cost requirements about different data that you want to do. So if you don't need to do pre-joins, you don't need to spend development effort of creating a sophisticated solutions how to transform, pre-aggregate, pre-join your data. If you use caching extensively, then you can allow a cheaper storage for your data. If you don't need to do data duplication and you can only go with federation, it means that you don't need to build like pipelines that constantly kind of like ETL your data in and out. And if you have elastic scaling, it also means that you only pay for an additional compute power when you need it. And it's kind of like boils down that you control the cost and not the cost control you. So data bus. Let's actually discuss this first because it's a nice abstraction to have. So we define like four data paths, and first one is ingestion spine. So it's literally how to get your data inside your Kafka. Another spine or lane, I'm a bit inconsistent with the names here, is historical lane. So it's when you get the data with your Flink and Spark, you can load into iceberg tables and then query with StarRocks federation and get the data for cold data. And then there is like a real-time lane. So it's literally kind of like just using StarRocks internal format to power your dashboards. And then there is a text search lane when we can get the data from Elasticsearch. So the idea is just super simple. Imagine that you need to support like some complicated ranking and filtering. What you usually do, you just go to Elasticsearch, do this preparation, then you get this data returned, and you do additional enrichments and joins with StarRocks and return the data to your users. Yes, it's just as simple as kind of like if you're proficient with Elasticsearch, you get the data into Elasticsearch, kind of like prepare the indices and whatever, and then connect to StarRocks, and you can write a single SQL query, and it just works. Then data tiers, so freshness tiers, as I call them. First, it's hot. That's where the data needs to kind of like be late as seconds. So it's basically real-time data. So you just get it through Flink directly through Kafka with optional transformation with Flink to StarRocks internal table, and then it powers your dashboards and APIs. And basically, when we are talking about dashboards and widgets, the expectation that most of the time you are working with the hot data, and that defines like a retention and the price that you are willing to pay. So the hot data is the data that you are willing to pay more because you need it more real time. Then warm data is basically kind of like a data over your Lakehouse that you federate through optional materialized view, because you say like, okay, this data is not as real time, but it can be at most kind of like as late as, I don't know, like 1 minute or 5 minutes or something like so. And I'm okay that this data can be late. So I can say like, okay, I can prepare it with materialized view, or just kind of like pre-calculate, and that's it. It's kind of like a little bit this. So then it's a deep history, basically cold data, and it's for the data for mostly immutable data. So for this data, we can process the data only once, prepare it in the most optimal format, and then just allow users to query it through StarRocks. And that's it. And now let's go to the most interesting part, like case studies. What we are talking about is homepage analytics. It was our first successful example that worked with StarRocks. So we spent some effort to assess StarRocks, to kind of like understand how to operate with this, to make it to make a deploy on our Katie's cluster, to gain experience. And then we need like a nice problem to tackle. And this is a nice problem to tackle. I remember I showed you the graph with latency P99, and this is about this. So this is how the widgets look. So it's recent sales, upcoming appointments, and other stuff. So what is the problem with this? The problem is very simplistic one. It's some kind of like aggregations. Usually it's 3-5 joins. The tables are big, so it involves bookings table, like sales tables. So this is kind of like around, I think like around 1 TB of data involved in all these kind of like queries. Maybe less, but yeah. And then we only need to support 2 months cut comparison. So basically you want to say like, okay, this is kind of like your revenue for the last month. This is how you perform now. And everything is called by provider. So all good. So what we decided to do, we decided to, okay, let's just do the most stupid thing that we can ever imagine. Let's just ingest this data into StarRocks and see if it would work or not. So we did it. And yeah, yeah, I should mention this one. So this is like a little bit of data modeling. So we have like a CDC data in raw tables. So it's basically like CDC data. We ingest it into StarRocks. Then we do some optional joins. They decided kind of like per models that we use. Then we define the recent window. And then we have like a final view that provides us this 2 months comparison using this recency model that we defined at the previous step. Very simple. Then what was the result? So we tried to just kind of like ingest this data into StarRocks, kind of like do the joins in StarRocks, no Flink, no transformations involved. Guess what? It just worked. I mean, like you can literally see by yourself. So before we were talking about P99. Now we are talking about P99.9. So we literally kind of like include more latency kind of like breakdown here. And you can see that we no longer have errors. There is a kind of like a bunch of errors like on July 1st or 2nd, but it's not like a timeouts. It's just kind of like we were experimenting with ways to deploy StarRocks, and something went wrong. Then we get these exceptions. We fixed it, but still it's kind of like a little spoils this nice diagram. But yeah, so as you can see, so before, for some providers, P99.9 was taking around from 10 seconds to 15 seconds, and most of them, they were actually timeouts. But then, once we introduced ROCs in the most simple setup, it's taking at max 300 milliseconds. So it's fast for everyone, even for biggest providers. So it doesn't depend on the size of the provider. We no longer thresh Postgres buffer cache. We no longer have timeouts. This is another kind of like view because, as I said, I think like P99.9 is a nice metric to boast, but we need to actually assess like more Ps, let's say. And usually kind of like latency for these queries is around like 60 or 80 milliseconds at max. And yeah, so it's kind of like the worst case scenario is 300 milliseconds. And you can see that these queries actually have some filters and some kind of like an additional kind of like dimensions. So they all kind of like work. Some of them are better than others, some of them worse, but it doesn't matter, it just works. So results, it works, no failures. Postgres is not involved. We are not thrashing buffer cache, so uh, we can save some money on RDS as well. It hides complexity for engineers because another kind of like feature, it actually took us only 2 days to make it working. Why is that? Because StarRocks is MySQL compatible. So for our engineers to use StarRocks, it only means that you need some MySQL driver in your language of choice. And then you just write a MySQL query. I mean, like there are some differences, but obviously, but it just like works. So you send it, and you can treat it as a generic warehouse, like your Postgres, for example. All the complexity is hidden from you. And also, if you model the data correctly, and because we didn't need to do like super complicated modeling here, so we just kind of like lay it in views. And for engineers, it was like select star from this kind of like final view where the filter is like so. So it's just kind of like the most basic queries that you can imagine. Yeah, so let's go to a more complicated example. So this example is about payments log case. So this is kind of like more complicated because now there are more databases involved. I only drew kind of like 2 of them, so checkout and our main DB. But we are talking like about from 3 to 5 databases, I think. So what we need to do is to get the data from these databases into our kind of like event bus, basically Kafka. Then we need to have like a dedicated app that only does this pre-aggregation. And then when you do this pre-aggregation and preparation, do all these crazy joins and modeling that your business requires, you get into warehouse database. And then you allow users to query from this database. This case is a little bit more complicated because, okay, this is like different data sources involved, because previously we were kind of like talking only about a single database. And now we are talking about like 3, 5 databases. So yes, we decided to do almost the same. We just got all the data into StarRocks and try to do the joins. The amount of joins here, it was about 20 to 30 joins, by the way. So it's not that easy. So we made it. We made it, and what had happened? It worked, but still, kind of like the performance was not in the range of SLAs that we decided to give to ourselves. So it was working in kind of like 3, 4 seconds. So then we needed to actually use Flink. And that's how kind of like it actually paid out our kind of like designing and architecture phase, when we said like, okay, we need to deliver like a platform, and this platform should be powerful enough to allow us to balance when we need to do some additional enrichments and transformation, and when we can go with only StarRocks. So we just kind of like pre-joined a couple of tables, a reduced amount of joins to, I don't know, like maybe 12, 15. And yeah, then we got the result. What result? I mean, like that. This is my favorite slide here, because it's one of our engineers is sharing like their first experience with StarRocks, and it's basically kind of like, okay, we made this feature to work, and previously kind of like using warehouse where all the data was pre-aggregated and querying it for the last 30 days. It's actually taking like more than 1 minute. And in StarRocks, with this kind of like most basic, it was before the optimization with joins and other stuff. So the report is loading for 4 seconds. I mean, like it's 4 seconds, so it's out our SLAs, but it's still very impressive because it just kind of like gets the data into StarRocks, make it do the work with joins, and kind of like 4 seconds for some of the people it would be completely acceptable and okay. Then you can take a look at the latency chart here, and you can see how we optimize the data. So first, it was actually taking like 10 up to 10 seconds. So it's not kind of like 4 seconds. Sometimes it was worse because the providers were big and you need to load the data from your cache. And then we made a series of optimizations. And right now you see this tail, and this tail actually shows that we are under our SLAs. And the average latency for these kind of like reports is under sub-second. So good. So let's go to the roadmap, because we have a lot of interesting things to do. We don't stop at what we achieved. We have a set of optimizations, not only related to StarRocks, but also kind of like to the stuff that we want to do. So we want to get AutoMQ instead of our MSK, because the more transformations we do, the more kind of like topics we need. And this actually means that we need kind of like more powerful and more cost-efficient Kafka. So this one, then Flux is, as I said, like we want our system to be very composable. And what it means that if the data for transformation is in Flink, then it's actually internal to Flink. And for example, imagine that we have dashboards that are actually using our biggest table like bookings. We don't want this data to be constantly kind of like for every single Flink pipeline to be present in the state. We want to externalize it and use it as a unified streaming substrate. Then StarRocks 4.1, because we want to have like workload isolation. So what it means, StarRocks is getting a lot of traction inside Fresha, and more teams willing to use it. But it also means that these teams can interfere with each other. So if you write an inefficient query, theoretically, it would be scheduled to run on multiple CN nodes, because that's the promise of StarRocks. And yeah, it would affect your working data. So first solution is super simple. You can have multiple StarRocks instances, but it doesn't make much of a sense. One of the features in StarRocks 4.1 is workload isolations with dedicated warehouses feature. So you can literally say this kind of like 3 CN nodes can be used only by this team. These kind of like 5 CN nodes are used for ingestion. These kind of like 10 CN nodes are used for real-time analytics. And when something happens in kind of like one set of CN nodes, another set of CN nodes are not affected. And then declarative pipelines. This is another improvement because we at data engineering are actually pretty efficient with working with streaming transformations and others. But I wouldn't tell that it would be that easy for ordinary engineers to write Flink jobs by hand. So we constantly experiment how to make it better. And we use new tools like Fildera, for example, very promising tool. I advise you to take a look. And data contracts, because now it's a question about like governance and kind of like who owns the data, how the data is transformed, how to track the dependencies about the data. So this is the areas that we want to be better. And I think like that's it. This is kind of like the end of this presentation. I hope you have a lot of questions that I'm happy to answer.
Yeah, we do have a lot of questions. Hello, everyone.
Okay.
Back. Yeah. Hello. Yeah. Let's first look at the audience chat. I think you can stop share. I can share my
Okay, sure.
screen, so you feel free to go to the chat and take a look. So okay. So first, let's take a look at the audience chat. We're gonna have time to finish everybody's question. We have a lot of questions. Okay. So the chat first. The first question is okay. For real-time laying and historical laying, are you back to the Lambda architecture? I think Emiliano really helped answer a lot of questions. Um, yeah, thank you so much.
Oh,
Um,
yeah. Thank you, Emiliano.
yeah,
I was not paying attention to the chat, but yeah, someone was doing the hard work. Thank you, Milena.
thank you, Emiliano. Yeah, I think this one is really well answered. Let's go move to the next one.
Hmm.
Uh, the next one, though, is MySQL front end. I assume storage is iceberg. I think we know how to answer this one too. Yeah, so StarRocks has its own internal format, which is its own storage engine, right? So that's columnar storage, managed by StarRocks tables, StarRocks metadata, StarRocks data files, right? And that has two modes of deployment: share nothing or share data, right? So you can either persist on local disk or you can persist on some kind of remote distributed storage, ideally object storage, right? And today, the performance with cache is very similar, right? And we're always trying to enhance that cache even for the most demanding customer facing like kind of workloads, to keep the SLA up, right? So yeah, so that's the our own storage, and also you can use something like Apache Iceberg or Delta Lake as your data lake, your single source of truth, right? And you can use stars to directly point to where the hell that metadata is, and we can directly query that and still get data warehouse like performance. Yeah, so MySQL is just a front end. We are compatible with the MySQL client, and we are compatible with the MySQL or standard SQL dialect, right? But underneath is something totally different than MySQL. Okay, so that's this. Thank you, Miliano. Again, thank you. Uh, are you using, I think this is a question for you. Let me put it on the stage. Are you using Flink rocksdb to manage state for transformation?
Okay, we are in Flink 2, so it means that we are using disaggregated state store to save space. So Flink is using like rocksdb for the state in general, but we are using disaggregated state store. I hope it answers the question, because otherwise we would get deep into Flink. But let me know if you want.
Yoko, let's do that. Next one, I missed one in the middle. I'm sorry. How you are superior to Apache Pinot, aka startree? I think there are many dimensions, right? I think federation is one part, right? That Apache Iceberg or that Lakehouse kind of integration. I think on the core, the biggest difference is the base performance, right? Apache Pinot or Startree is written in Java. it's very difficult to utilize SIMD instruction sets, to fully utilize the power of vectorization, right? Basically running everything in memory in parallel, right? In batches, right? And read every single CPU cycle in batches, right? And that when we implemented vectorization, I think that was like operator by operator 3 to 15 times performance difference with
Yeah,
SIMD.
and also joins,
So
I guess,
yeah,
like
and also joins. I think Apache Pinot also built the shuffling service, right? But you need a whole lot more to actually run those big queries, big big table, join big table quickly, right? Quick enough so you don't have to do denormalization. I think performance and federation and just the entire ecosystem, right? Um,
I mean, like
okay,
theoretically,
yeah,
Apache Pinot is more real time, but at the
hmm
same time, I mean, like most of the times you don't need the maximal real time. You need like an ability to kind of like query your data and
yeah,
join your data. So
yeah,
for me, it's kind of like StarRocks is superior in
yeah.
this example.
Yeah, you StarRocks, you can get like, sub 10-second data freshness with like upserts and deletes. And that's really, for a lot of the real-time use cases, that's plenty, right? Um, Let me see. There are still questions. Uh MSK? Oh, Amazon MSK, right? That's managed streaming
Yeah.
Kafka, right?
Yeah.
Amazon managed streaming Kafka. Okay. Next question. If you can answer this, what's your typically monthly cost for using StarRocks?
Our data one? No, we're actually using our own deployed on KDs,
Hmm.
StarRocks.
If you can
So
share this, if you can share it, it's fine.
Uh, I'm actually don't know the current cost. I mean, like we run a series of optimizations because first we were running StarRocks 3.5, and in StarRocks 4 there are a lot of optimizations around like working with object storage. And once we deployed StarRocks 4, we reduced our cost for storage like 10 times.
Hmm.
And right now, I think like the cost of running like StarRocks is maybe 2K per month, but I think like Emiliano can share this one because he's responsible for the cost on StarRocks and monitoring this stuff. I'm the person who optimizes these costs, but
Yeah. Next question from Alberto. Have you compared the different ways to connect Kafka to StarRocks? I mean, just tree to
yes,
StarRocks. Yeah, Kafka Connect versus Flink versus routine load with it versus like
yes,
what is the
yes.
download
We
speed?
actually kind of like run a series of experiments. Right now, we are using Flink as our main way to ingest data into StarRocks. If you
Mm-hmm.
are curious, you can go to our Fresha data engineering blog, where Nicoletta had a series of two articles. First one is getting like a historical data inside StarRocks with pipes, and another one is assessing like what is the best way to get the data, streaming data into StarRocks. And we've chosen Streamload with Flink. So if you're interested, like it would be a whole bunch of information.
Mm-hmm. Thank you. I was trying to look for the block. I remember seeing it somewhere. We can share if anybody has that. Let's share it in the chat. This is just a chat. We're not even Q and A yet. Uh, okay, I can't find it right now. Sorry, it's
Okay.
4.0. I'll put it on the stage. Yay, try 4.0. Now let's go to the Q&A. Okay. So first question. You said, I think this is where your page 9 is, right? So you said 3K requests per second. Right? So what kind of requests are those?
Okay, let me share the link to Fresha Data Engineering if you wish to follow.
Hmm.
3K requests,
Thank
what
you.
kind of requests are referring to as a request from the dashboards frontend? It's actually just kind of like the request that we operate on. So it's kind of like an absolute metric. So for dashboards, it's hard to actually calculate because we have requests per dashboards, requests for widgets, requests for payments log case. So you need to actually aggregate this data. So I don't know how much requests, and we are constantly getting like more and more use cases for the StarRocks. 3K request and kind of like CDC events is just kind of like the whole set that we operate on. And bookings is just our biggest table. So it's a comparative metrics.
Hmm. Thank you. Next one. Why did you choose to use Python as the table format, and why not only just use Iceberg?
Oh, this is a complicated one because first, I mean, like all my journey with this data platform, it's actually started with Python. So I
Hmm.
got interested into Python, so I kept kind of like researching. Then I discovered like flows, and only then I discovered StarRocks because our initial idea was to use ClickHouse. And ClickHouse, though it's an amazing engine, as I said, like we run a pretty sophisticated analytics with a lot of joins involved. So first I thought like, okay, we can solve it with ClickHouse, but we need like a transformation layer with Flink. And that's why it's all started. And then in the middle of this kind of like architecting, I discovered StarRocks and I said like, well, but it's better. I mean, like arguably better. I tried to use it. It worked for me. And then I said like, but it's actually saving us a lot of effort because it's kind of like a very, like easy pattern to follow. So I just ingest the data into StarRocks, measure the base performance, say that I like it or not, and only then I need to optimize it. And it's not like with ClickHouse to kind of like, okay, I need to develop this dashboard. Now, first I need to develop all this set of complicated pipelines, then only then I get the data into ClickHouse, and then I only assess if it works or not. So this is kind of like a long cycle of getting the data into ClickHouse in a proper way, just to assess like is it kind of like acceptable performance or not. With StarRocks, as I said, like our kind of like pattern of working with StarRocks, get the data into StarRocks, get the base performance, optimize later. So it's kind of like
Yeah,
an easier and more sensible way of working. And imagine
yeah.
if we kind of like, yeah,
Yeah. It turns out like after 40 years, the relational model is still pretty good now. Yeah, still need relational model. You still need joins. Yeah. Yeah, so I think the ultimate reason, for Python, if I understand correctly, is that so you started with ClickHouse, and then you needed stream processing, right? You needed Flink, and Python's in the streaming kind of right. It's really compatible with Flink, right? It's
yes,
basically
yes. The first
Flink
idea,
table, Flink
yes,
table,
yes.
and yeah, and then you figure out like actually we need joins, and then we live with this. So
Yes, exactly. Because the
yeah,
first idea was okay, we need data more real-time-ish. So
yeah.
kind of like what we can use. And I thought like, okay, let's use just Python because it would allow us to get data more real-time-ish. And
Mhm.
then we have an easier time to transform this data with Flink and whatever, because Python is closely related to Flink still. And then we discovered StarRocks, and right now Flink, kind of like Python is still kind of like our format, but our approach with working with data lake is basically, okay, if the data is warm or cold, we just offload it mostly to Iceberg. And the idea how we operate with Iceberg is very kind of like conservative. So we say
Mhm.
like, okay, for the last, for example, 2 months, the data is in StarRocks internal, and we can query and rely on the performance of StarRocks. And only when we need data like, I don't know, like more than 2 months is old, we say like, okay, then we need to go to Iceberg and union this data, so we can get like, okay, if I only interested in real-time data, I only query StarRocks. If I'm interested only in cold data, I only federate to Iceberg. If I'm interested in a mix of hot and cold data, I query first part of the data from StarRocks and then union with the cold data. And it's all in a single query. So it's very easy to kind of like reason. It's a single way to work with the data.
Yeah, that makes sense. Thank you. Thank you so much. And next question. What is the size of your largest table in terms of rows and bytes? What cluster configuration are you utilizing?
Okay, that's an interesting one. The size of the largest table in terms of rows and bytes. I think like it's definitely bookings table. So the last time when I checked bookings table, it was around 200, 300 gigabytes of data, like in Postgres.
Hmm.
Cluster configuration that we are utilizing, well, it's shared data mode in StarRocks. We have up to 25 CN nodes. these CN nodes hold around 30 gigabytes of RAM, and we have around 200 gigabytes disk as a cache. I hope that's what I asked about.
Yep. Thank you. Next question. How does elastic scaling affect the query response time and query queues?
Another great question, because this
Yeah.
is kind of like, as I said, like CN nodes are stateless. So in
Mhm.
theory, kind of like firing a new CN node is not that complicated. The complicated part is cache.
Mhm.
So what we found out that when we need to get like new CN node into our cluster, we need to wait until the cache is filled. So then the response time it's actually deteriorates. It's getting slower. So what you can do with it? You can literally kind of like say that you need to pre-warm the cache before making this new CN node available. Or what we are doing right now, you can say like, okay, we have 25 PVCs, like basically disk caches, and when CN node is not used, CN node is killed, but PVC stays alive. And when this CN node is needed another time, it just connects to this PVC with a little bit out of date cache. And then you need to spend some time to load the data from your object storage or from another CN node disks to get this cache up to date. So there would be still a bit of response time deterioration, but it's kind of like minor.
Thank you. Let me see. What's your use case for having historical and real-time lanes? Just the
Wow.
two data path,
Okay.
like which
Payments
each
log.
one serves.
Payments log is kind of like the most easy example. So
Yeah.
basically, for dashboards and the kind of like showing the first page of payments log, you're interested in real-time data. So it should be fast, just to load the first like 1, 2, 3 pages of this data. But then when you go to kind of like the data, because it's payments log, so sometimes you want to investigate some complicated use case and you need to go like 2 years ago. For 2 years ago, it's completely acceptable to not have like a response time of 1 second, but it's
Mhm.
completely acceptable to take like 3, 5 seconds. And this is kind of like the use case for cold data. You just go into Iceberg, you fetch the data from it, and that's it.
Thank you. Next one. I think we did this one, right? Different ways to
Uh,
connect. Yes. I
yes,
think we did.
yes, I
Yes, we
think like
did.
we did.
Yeah. Next one. Maybe more for SLAs. Do you see a data size limit for StarRocks? I work with multi-terabyte tables. Um, for no, there's no limit for how big is MPP. You can scale horizontally as big as you want, and the query can scale, right? Because we're able to shuffle all of the right data to the right nodes. So all of the nodes can work together for any kind of operation you do, any query operation you do, aggregations
Yeah,
or joins, right? And the biggest cluster I've seen Starks running uh, are around 10 petabytes, 300-400 nodes each with like I think like 50 cores or something, 50-80 cores or something, crazy big cluster. Yeah, so definitely multi-terabyte tables, it shouldn't require much tuning, should work out of box,
but
if
also
you
kind of like,
provision your cluster size correctly. Yeah.
yeah, also multi-terabyte tables. Okay, you have a big table, but it can be scaled for some kind of like clustering key. So for example, in our case,
Yeah.
bookings is a big table, but we still can scale per provider ID, basically per partner. And this
Yeah.
means that that's only kind of like a dedicated CN nodes, you can collocate joins, and it would
Hmm.
be only operating kind of like on a single CN node, and all the data would be kind of like local. In this sense, I don't see like much of a limit.
Thank you. uh Last question from the audience. What are the roadblocks you encounter migrating to Starbucks compared to your Snowflake setup?
Well, a lot of. I mean,
Yeah.
like, it was a new technology,
Mhm.
so we had like curious cases when we kind of like didn't know what was happening with our cluster. So sometimes, yeah, it basically boils down to our inexperience with the new technology. So the cost, I mean, like we were surprised to find out that our cost just skyrocketed because we kind of like deleted a table, but the metadata for this table was not deleted, and it was kind of like trying to download the data from for this table, non-existent data, from object storage. And the object storage, we kind of like ended up paying, I don't know, like around like thousand or $2,000s only for the list request. So it was unexpected. It was kind of like new, and it took us some time to discover. And then it was a question how to solve this problem. But yes, compared to Snowflake, you just pay for the Snowflake and you get like a service. And as I said, like in our use case, we actually decided to deploy StarRocks by ourselves on Keras. We needed to be more proficient with this way of doing things. We needed to kind of like reason how to use it. Also, we needed to kind of like adapt our workflows around StarRocks because we have all the analytical data models in dbt for batch analytics in Snowflake. And it was like a completely new set of challenges to say like, okay, does this kind of like modeling suits real-time analytics? Because before it was kind of like, okay, I materialize this kind of like data once in 20 minutes. And right now it's kind of like, I need to run this in real time. I need to do these joins. I don't need to prepare the data. I need to execute the query. And also there would be kind of like a new article by Fresha Data Engineering released when we share our experience about like how modeling has changed and what we needed to adapt from Snowflake to StarRocks, because we want to our models, analytical models, to be comparable between BI and real time. So this is kind of like a very unexpected. It's still technical challenge, but it's a very unexpected dimension of challenges. So if you're interested in this, I advise you to take a look. But yeah, it was kind of like we needed. Snowflake is kind of like a vendor, and CelerData is also vendor, but we decided to run StarRocks on our own Keras, and it's a whole different experience. I mean, like most probably running on CelerData is kind of like a nice experience that we had.
Thank you. And actually, there's one more question. It's a short one.
Mhm.
StarRocks is written in Rust? No. It's the front end, basically the metadata management for our internal table, connecting to external catalogs, reading metadata, right? And query planning, that's written in Java, right? And all of the query execution are CN nodes, compute nodes, horizontally scalable, stateless. Those are written in C++ for performance reasons. Okay, that is all of the questions that we have, and I actually have one question. So you mentioned in your slides you have 20 table joins, right? What is like the scenario? Is are those like joins common? Like one query that has like 20 joins, 20 tables together.
Well, I mean, like the scenario is basically because it all comes from. I'm sorry, my AirPods just decided to go out of my ears. So this scenario is pretty common because, as I said, like our story was first we had BI analytics. So
Mm-hmm.
this BI analytics, it actually allows you to do layered like models in dbt, and these layered models
Yeah,
they're kind of like nice to write, and in the end it's a kind of like just select something from this kind of like model, but it creates a lot of unnecessary joins, a lot of subqueries, a lot of like conditions to support. So
yeah, that makes
it's
sense.
it's mostly related to how we model the data. So sometimes it's not necessarily needed to have like 30 joins, but it's just kind of like first iteration just to translate these kind of like queries. It's kind of like 30 joins. Then we start like then we deploy it, for example, into StarRocks, and we say
Mm-hmm.
like, okay, it works. We are not happy with the performance. What we can
Yeah.
optimize? Then we discover like, oh, we don't need this join. Okay, we remove this join. Then we say like, okay, we cannot remove this join, but maybe we can transform this data with Flink and flatten this before getting into StarRocks. And then
Mm-hmm.
kind of like with this set of optimizations, we constantly get our kind of like query more optimal, reduce amount
Mm-hmm.
of joins. But yeah, sometimes it's still kind of like around 30, 50 joins. it's not that uncommon. It's
Okay,
around
if it
payments.
works, if the database can handle it, why not? It's right. Yeah. Okay. Okay. Then that actually make a lot of sense. Thank you. I thought those are like raw tables. I thought, what is your data source? It's crazy. Okay. That's I think all of the questions and everything we have. We ran for an hour and 7 minutes. Thank you guys for joining. Thank you, especially thank you, Anton, for giving this amazing. Oh wait, are you using the same Snowflake DBT model in StarRocks?
Uh, in a sense, so we kind of like use dbt StarRocks. So well, I think like I should just mention. So as I said, like we first kind of like want to have the models that are comparable between StarRocks and Snowflake. So we just get the same dbt models that we have in Snowflake, model these models in dbt StarRocks, create a view, and then we provide this view for querying. And then it's a different question how we optimize these views and intermediate kind of like data models. But
Hmm.
it's I think like we will share more details about this. But yes, initially we use the same models that we built for Snowflake to StarRocks just to speed up the development. Then we optimize it pretty heavily.
That makes sense. Thank you. And thank you so much for the great presentation. Thank you, Emiliano, for helping us with the question. And stay tuned for their blog.
Yes, thank you.
Soon we'll be publishing about queries in StarRocks. So stay tuned. We're gonna amplify that through our channels too. Yeah, thank
Thank
you.
you.
Thank you so much for joining. Thank you for the great presentation. Thank you for the great answers. Thank you for the great everything. Right. See you guys again next time. We're gonna keep running our European series in this time zone. Yeah. Stay tuned, guys. Thank you. Thank you so much for joining. Thank you. Thank you, guys. Bye. Thanks.
Bye bye. Thank you.